you're going to see it. So what you're doing, like in the Monte Carlo, when you wanted to just sample from this backup diagram, you start from one state, and then you sample one action, and then you sample the next state, and you're going to stop when you get into the terminal state, right? Meaning that if you come here, you're going to have a short trajectory, but you could have a long trajectory as well. And you only, I mean, the idea could only concretely work if you have the terminal state at the very end, right? But now you don't really need to do that because, like, you always need to sample one time step in order to be able to estimate your current value function, right? So you just sample here. Oh, okay, next state is 0. So sorry, terminal, so it's going to be 0. But what if that happens? It's okay. You're going to again stop here, and you're going to rely on the estimate of the value you have for this particular state, right? And if you keep doing this for all these states over and over, this is gradually going to converge to what you want, okay? So this is the idea of bootstrapping, as I said. So each time you're just sampling one time step next, and this is going to give you a kind of estimate for future. Now, what we do in practice, of course, we're not going to just sample one single time step. We're going to, again, sample a long trajectory, right? And then, similar to the Monte Carlo approach, at every single time step, you can look at the forward as your next time step, right? And then you can estimate the value of the state in that particular time step, right? Again, you go for the next one. Well, what is the next state? I'm going to estimate the value of this guy. And so on, I'm going to go forward, right? So we're going to start from some initial value estimates, and then we're going to sample one complete trajectory. So if I have the complete trajectory, each time that I want to estimate the value of this state in one particular time step, say the value of this state here, I am going to just collect the immediate reward plus the estimate of the value of the next state, right? And so on. Then I go for S1. I say the value of S1 is going to get updated by the immediate reward and the value of this state in time 2, right? And then I keep on going forward in time. Now, if you go over this trajectory, one particular state might get updated multiple times, right? You agree, right? Because you might be in a state 0 here, and again somewhere in between here and here, right? This could happen, correct? So you could have one state updated multiple times, and this is totally OK, right? Exactly like the Monte Carlo approach. So you're going to just simply go over it, and then you update using the bootstrapping idea. This is what we call a temporal difference, right? And what we are talking about right here is technically temporal difference 0, TD0. You're going to see how you can expand it. You can guess. Instead of just one time step, you just go 2 time steps, right? Or 3 time steps. Always you can write value at any state, reward plus reward plus reward, value afterwards, right? You can always write it down. And if you do that, you are basically doing temporal difference. Because you're going to say, what is the value here? I mean, if I know what is in a bit future, then I can just explain what is the value here, right? And you use this temporal property in your trajectory to find an estimate or update the estimate of your value function. So here is the temporal difference evaluation for one given policy. So we're not talking about one particular state anymore. So I give you the policy. I want you to evaluate it. And if you want to use TD, you're going to use this one, right? So you're going to start with all the values being 0 initially. So every state is 0. And then you just sample one trajectory. I have this trajectory. Then I start to just go over it in time, right? So I start with the first guy, S0. I say value at point S0 is going to get updated. So this is the previous value before I see it. And then this is what I get. So R1, the immediate reward, plus value at the next state, which is S1, right? I'm going to update with this value, right? Now I go for S1, right? When I go for S1, I can update the value of S1 based on the immediate reward and value of S2. If it happens that S2 is exactly the same thing as I had at S0, then I have already one estimate, right? So S1 value is going to get updated, right? And I can keep on going like this. Again, if I have too many episodes, and I keep on with this approach, eventually every value that I have in this environment is going to get updated, right? And then it gradually converges to one specific function, which is hopefully the value function that we want. Now, one key property that you see here is that when you want to update in TD, you eventually don't need to wait till your trajectory is over, right? In Monte Carlo, it was correct that you can update after every single trajectory. We did online averaging to do that, right? But still, if you want to update, you need to sample the complete trajectory, right? Then you start from very end, right? You would say this is 0, RT, RT minus 1 plus RT, and you go backward, right? That was the idea, right? This is the way we update it. But here, I don't know, right? I don't need, because when I am at time 0, if even this guy has not ended yet, I can simply use R1 and the estimated value of S1 to update that value, right? Yeah, this is giving us more sort of online approach, and we are going to use it later on when we are just talking about online control, right? But this is important to pay attention. This is actually completely online now, right? So as you are just sampling one trajectory from the environment, you can improve your idea about the values, right? Your estimates of value. Okay, now you can obviously use the same idea to update or estimate your action value function. This is the same thing, only you just go for 2 dimensions, right? Again, what you're going to say, okay, Bellman equation is telling me that the Q function at one particular state in action is the average of the immediate reward, right? The immediate reward that I get for that state in action, plus the expectation of the value in the next time state, right? Next state, sorry, right? And what you can do, you can simply treat it as a kind of estimation problem, and then you estimate those expectations simply by averaging, right? And if you do online averaging, this is going to be the expression you end up with. You want to know what is the, you want to update your Q function in one particular state in action. If you want to update this guy, you would say, okay, what is the immediate reward I get? What is the value in the next time step, right? That value in the next time step, please the immediate reward is going to update my Q function, right? Everybody's clear? Questions? No questions? So again, similar to the Monte Carlo approach, if you use this approach to estimate the Q function, and the same approach to estimate the value function, V function is going to converge faster, right? Because you have less parameter, you have only states, you're going to converge faster, right? Here, you need to see enough pairs of actions and values, and states, right? And because of that, it's going to take longer time. Okay, so this is the action value estimation using temporal difference. Again, you start to just collect a bunch of trajectories. In every trajectory, you can update every single pair. So I have seen this guy, then I have seen this guy, and so on. So I'm going to average update based on immediate reward and whatever I have afterwards for that Q value, right? Questions? No question? Everybody's cool? Okay, so dummy grid world, you can try it at home. It's very simple. I mean, again, you're going to converge after 1 or 2 iterations. You're going to see, even if you start from 0, this is going to converge very fast. Because eventually when you play, like you start from everybody being 0, and then this guy is going to end up with the terminal, and then you get the right value for it, right? And then you go on for the third one, this corner one. Again, you're going to get the right value, and then this is over, right? So you just play with a random policy, and you just meet enough number of times, 10, 15 times you play, you get a rough, good estimate of the correct value. Okay, that's it. Again, similar to the Monte Carlo approach, you're going to see this behavior. So if you want to know how well your estimate is behaving as compared to the true value function. This is going to drop as you increase the number of samples. This makes sense, right? You have more samples, you are getting better estimate, right? Your estimate is getting less noisy. That's obvious. The other thing is that this against alpha, again, this guy is showing this kind of behavior, right? So if you are updating online, then if you choose very large or very small choice of step size, alpha, then it could lead to bad estimate, right? So again, you need to tune it. This is a kind of hyperparameter tuning for your algorithm, right? That's it. So, questions? No question? Okay, now, to just give you the idea why bootstrapping is doing better as compared to the Monte Carlo approach, I have the dummiest example ever you can think of. So it's even dummier than the dummy grid world. What is the idea in this game? In this game, this is a very exciting game. So you have just one key here, this key. If you can press this key, and each time that you press the key, you see one color on the screen. Okay? If you press this one and you see green or blue, like each time you press, you're going to see either green, blue, or red. Okay? If you see green or blue, you can keep pressing. If you see red, it stops. Okay? And now, each time that you press, you are going to either get 0 or 1, right? 0 randomly. You don't know really. Just you press, you're going to get reward 0 or 1, and you keep on pressing. Once you see red, then you cannot press. If you press, you get nothing. You're going to stay red. Clear? I know it's extremely dummy, but it's going to explain what is the difference between Monte Carlo and temporal difference. It's going to clarify why temporal difference could be of better performance in such a case, in environment with few episodes. So now, the states that you have are green, blue, and red, right? So it's the color that you see on the screen, right? If you see green or blue, you can keep pressing. If you see red, it's going to stop. Action is actually just one. You don't have any choice. You just press, right? So there is no action, really. But you can say that you have just one action, and that is just pressing, right? So single entry state set. So now, one thing before we go on. I have this green and blue state, right? Do you think that the value of these two guys should be different? Or in green, blue or green, it doesn't really matter. You can keep on doing the same thing, right? And when you keep on doing the same thing, you're going to always see a random reward coming, right? So technically, if I just get green and blue and merge them into a new color, I don't know, purple, then I have purple and red, and the only difference is that when you are in purple, you can keep on playing. When you are in red, you stop, right? So green and blue should not be different, right? So you expect that you see roughly the same value for them, right? So when I am in this state, I expect to gain something specific. If I get to red, it's a terminal state. I'm going to stop, right? So you have this expectation from this simple world. And then let's consider one particular sampling. So we don't know the distribution, so we're going to sample, right? So I start playing. And when I keep playing, I'm going to just see blue, I press, blue, I press, I get red. And you see the rewards that I get, 1, 0, right? Again, I play once again. I see blue, I press, I get 1 reward, and then it stops, right? Again, I start playing blue, I press, I don't get nothing. Again, it's blue, I press, I get 1, and then it stops, right? I try playing this. Here is 1, 2, 3, 4, 5, 6. I have 6 different trajectories, right? And as you see here in the trajectories, most of the time I'm seeing blue, right? But once I see the green one, right? Now, can you claim based on this observation that green is happening much less than blue? Well, maybe you can say, but it's not going to impact the fact that the value of seeing green or blue is the same thing, right? Correct? Okay. Now, you see this. Let's start just estimating the value of every single state using the Monte Carlo approach. If I want to do it by Monte Carlo, how can I do it? for blue first. For blue, can you tell me what is the value of blue? How many samples of blue I have? I don't know personally. So here is one blue, right? Second one, right? Third one, fourth, fifth, sixth, seventh, eighth, right? We have 8 different samples of blue, right? Right? Now, what is the future return for the first sample? What is it? Or G of, yeah, G1 of blue. Can you tell me? What is it? If I look at the very first blue, I play blue, then I get 1, then I see blue. I again keep playing, I get 0, stop, right? So anything that I'm adding up, discount factor is 1, okay? It's going to be 1. What is G2 of blue? Can you tell me? It's 0, because the second blue, when I get in the trajectory to the blue, I press, I get 0, then it stops, right? So it's going to be 0, right? What is G3 of blue? What is it? It's again 1, because this is the second trajectory. I press blue, I see blue, I press, I get 1, then I stop, right? So this is again 1. I can keep on writing it down. Can you tell me what is G8, the last one of blue? It's again 0. Great. So you see it. So if you do that, you eventually have 4 different cases where you are at a state blue and you collect reward 1, return 1, and you have 4 different cases where you collect 0. So your Monte Carlo estimate is half, right? Everybody's cool? Now, when Monte Carlo estimate is half, what it tells you, it means that it says, like, whenever you see blue, half of the time after that you see 1, half of the time after that you see 0, right? Right? And roughly speaking, you are going to collect half in general, right? Till you finish, right? Now, you expect to see the same thing for green, right? Because when you are in green, you're in this case green, then there is no reason for this environment that gives you a different kind of behavior, right? But the whole issue here is that if you estimate it based on these samples that you have, what do you conclude? 0, right? You're going to say I have 1 sample of green. I have collected only 0 after that. So my green is going to be 0, right? But this 0 is not coming from the fact that really I have seen lots of samples where green is always, whenever I see green, after that for always I get towards the terminal state with no reward, right? This is not because of that. This is because I have been inside green once only, right? So I have just 1 sample, right? So this estimate is very poor estimate, right? Whereas this guy is much better, correct? This has 8 different samples, right? So its variance is by factor 8 smaller than this one, right? So it is very high variance estimate. Now, what's going to happen if I use TD? What's going to happen if I use TD? Okay, well, for blue, it depends on how I update, right? Where I start and where I end. But if you choose the right value of alpha and you keep updating, like initially you would say, oh, here is going to be 1 plus value of blue, right? 1 plus value of blue equals 0, so it's 1, right? Next time you're going to say blue, I am here, it's going to be 0 plus difference to the value of red, right? The value of red is 0 now, right? And then you can roughly say that you had 1 and now you have 0, so now your estimate is going to get updated to half, right? And you keep on updating, you're going to go up and down till it roughly converges to half, okay? This is why I put it approximately half, because it's not necessarily half when you use TD, but you get roughly to half if you choose right choice of alpha. Okay? Now, you got to half. Now, if you are, say you are at this point, right? So you're updating. You start from here. You can immediately update, right? Initial value for blue is 0. TD would tell you, okay, immediate reward 1 plus the value of the next state is 1, right? And then you get here, now you have 0 plus the value of red, which is 0. You're going to average it with whatever you had before. It's going to be half, and you keep on going like this, right? So when you keep on going, at this point, at this blue, you have again updated your value, and now it's half, right? Now what's going to happen when you get to the value, to the green state, and you want to update it? What do you do using temporal difference? The estimate for value of green, you initially started by 0, right? You're going to update it, and this is going to get updated with what sample? Immediate reward, which is 0 plus value of the next state, which is blue, right? So this is going to be the way you update it, right? You're going to say, okay, this guy was 0 before, right? So the current value of this estimate is 0, right? And then you have here 0, and immediate reward is 0. That's fine. The value of the next state is blue, right? So you're going to be roughly half, right? And you're updating your 0 estimate, so this is not going to show up. This is going to be roughly half, right? Everybody's clear? So here, you're getting more reliable result, right? Yes?
What does that alpha mean again? That was there in the TD equation.
Here, alpha, I guess I put it 1, right? No, alpha is not discount factor. It's the one which you update with. So if you remember, like if I have estimate up to time, say I have k samples, right? If I estimate with k samples, then my estimate, say mu k, I can write it down mu k minus 1, my estimate by k minus 1 samples, plus alpha times my particular sample that I have, say, for example, this is G or whatever, right? G of the new sample. This is the new sample that I collected minus whatever I had before. So it's going to be mu k minus 1. Right? This is the alpha. And this is something between 0 and 1.
Right. This is that usually it's 1 over k 1.
Yes, you could put it 1 over k, right? And if you put it here 1 over k, because you have one sample for green, then it's going to be 1, right? But this is really not a kind of mandatory choice, so or even optimal choice. So you can play with it, right? But here I simply put it 1, right? But even if you just put it something else, you are going to end up with some non-zero value, right? Which is giving you less variance as compared to just relying on a single sample. Questions? No question? Okay. So now, what I showed you in this example is actually a general kind of property that this TD and Monte Carlo approaches have. So what we do in Monte Carlo, we are really not caring about whatever happens in between, right? Every time we want to update or estimate, we're saying that I am in this state. Let's see what's going to happen towards the end, and then I get that sample I update, right? Correct? This is the way that you update. This means that you do not care what happened in the way, right? But when you use TD, you are looking on what happened on the way, right? You would say that, oh, I was here, right? And at the green point, and then I just went one step further, it was blue, and then I got to the terminal state, right? And it's true that in this particular sample, I just collected 0, but I do know that in average at blue I am collecting half, right? So maybe this time I collected 0, maybe next time I collect 1, right? And then I rely on the estimate of the blue, right? Now, what is happening here is that eventually you are somehow implicitly using the fact that your environment is just describing a Markov chain, right? Because you would say whatever happens next, right, is carrying the information, right, with it. And then based on that, I can say that, okay, well, if if I know what is going to happen afterwards, maybe I can use it, right? I do not need to throw it away and simply rely on a single sample that I have towards the end. So that is a sort of thing that you can say. So this, I think I have mentioned it here. TD approach is using the Markovity of the environment. It says that it's a kind of process like Markov says that when you are at green, right, then there is one probability to go to blue, right? And then when you're at blue, again, there is one probability to go to red, right? So you don't care about the fact that you were second last time step at green, right? And because of that, you are somehow cutting the memory in between, right? And using this fact, this TD is giving you a better kind of estimate. So here what you see is that Monte Carlo is assuming that from green, you're getting to red with reward 1 with probability 0 and reward 0 with probability 1 because it has only one single sample. And in that single sample, this was happening. But in the temporal difference, this is not the case. It says that, OK, this is true that I have one sample from green to blue, but from blue to red, half of the time the environment goes with reward 1, half of the times the environment goes with reward 0. So maybe I can use this fact, right? So this is the kind of property that makes the two approaches different. This does not mean that TD is always the best thing ever. So you don't really need to think like that. So if you have crazy large number of samples, or you have a very weird kind of observation set, which is somehow not related too much to what really happens inside the environment, sometimes Monte Carlo gives you a better estimate. Okay? Now, the thing that I want to tell you here, I don't expect you to see it immediately. This is only to tell you here, in case some of you are interested to read more about it or have some background on that. So one thing that people say is that TD is using maximum likelihood estimate based on the Markov process, right? So what it wants to do, somehow, it assumes that from one state to the next state, this is always described with one specific distribution, right? And then it says that I have so many samples of this distribution. Let me estimate that distribution implicitly, not explicitly, implicitly, right? Somehow behind the scene, TD is doing that. And how you can estimate one distribution, the best approach to do is maximum likelihood, right? So it is somehow doing that. But Monte Carlo is just not doing this, right? So it says, who says that necessarily there is a Markov chain happening here, right? We talked about it that a real environment should always have Markov chain property. But the key point here is that you need to make sure that what you are taking as this state is really this state, right? We talked about it, right? We said that maybe something that we see and we call it a state is not really this state, right? Maybe there are some information behind the scene that we do not have access to, right? For example, in the case of stock market, right? How you can say that all of those information you listed, like the, I don't know, those liquidity and those stuff. I mean, people who are in finance know better. So market margin, those stuff. Who says that those information are really describing this state, right? Maybe there are something that you don't know about, no one knows about, right? Nobody claims that they know really what is explaining this environment, right? So because of that, Monte Carlo is somehow saying, OK, I'm not sure if this is really happening because I don't have access to the Markov chain, so I forget about it, right? So I only rely on the samples that I'm getting towards the end. And I just use them, average them, to just estimate my value. This is eventually what we call it this score estimate, right? And there is one key factor here is that this guy, the maximum likelihood, could give you a smaller variance. It means that when you just estimate your value function, your value function is going to start jiggling up and down faster, right? But it could be biased. Like you might, instead of converging to value 1, you converge always to value 1.2, right? But you are slowly jiggling around 1.2. very fast, right? Whereas in the Monte Carlo, you are not biased. You are getting exactly to 1. But your estimate is just changing with high variance. So like the right value is 1. You're getting to 1. But the estimate that you get with your samples are 1.5, half, 1.4, 0.6, and so on, right? You slowly get there, right? So this is a kind of trade-off that these two have. But as I said, this is not really impacting your understanding of the course. So if you don't see it, that's OK. Just wanted to give you, like maybe sometime in future, somebody appreciate that, right? OK, cool. So now, one other thing that I want to just tell you about this, this model-free approach is since we are using samples in the data, samples from the environment, it might be the case that going over your data multiple times is going to improve your estimate. So it doesn't mean that if I just took my episodes and updated my values, right, or estimated my values, I should throw them away. You are going to see it when we get into Q-learning, where you can do buffer replaying. But right now, you can simply see it also in this example. What's going to happen if I want to use TD, but instead of this order that we had before, I have this order in my sampling? So I start sampling the environment. First time I see green, it goes blue, red, it stops, and then I get all the other trajectories. What's going to be the estimate of value at green? Yes? 0. It's going to be 0, right? It's going to remain 0, and you go and you update your blue value towards the end, and you get roughly half, right? So this is going to happen when you have the other sorting in your data, right? But now, if you go once again over this data set, what's going to happen? If you go once again over this guy, then this one is going to get half, and that again, right? Because you are 0 here, you again start from green, and now you're going to say, OK, I got 0 plus value of blue, right? And the value of blue is half, so I'm going to update my value, right? So you can get roughly again to half, right? So just to give you this idea, it's not necessarily the case that you just use one trajectory once. You can use it multiple times. And each time you go over it, maybe you have a better estimate of your value. Now you are looking at it from a different perspective, right? It's like you don't like a meal, but today you are very hungry, right? So let's look at it once again. You can see. So yeah, now just a few notes here regarding the quality of your estimates. As I said before, the quality of your estimate depends on many parameters. So for example, this alpha value that you see is the one with which you are updating. And if you use different alpha values, you're going to see different convergence rates, right? So this is for the Monte Carlo. This is for TD. What you see here is that your TD is dropping in the error quite faster. This graph that I am showing for you, sorry, I should have mentioned this. So I told you the dummy grid work, right? Now you just increase it very large. You start moving it in it randomly, right? This is the random one, okay? And now you want to know what is the value of every single cell in this environment, right? And you can compute it using the Bellman equation and model-based approach because you know the environment, you know the policy, right? Now, if we do that and then we estimate using Monte Carlo and TD, then you can compare to see how much error you have. Now, what you see about TD, you see that the error is just dropping down quite fast, right? This is what I told you. You have a small variance. So it's going to be the value of one particular state is maybe high, goes down, and then gradually it's going to get to some value, right? But that value that you get, it might be slightly different from the true value, right? Whereas this guy is dropping slower, right? But it can lead you exactly to the value that you have, the true value. Okay? So this guy, the red guy, the Monte Carlo, has higher variance, right? It's like starting high, going down, again, going high, it's not coming down that fast, right? You need so many samples to get down. Okay, so yeah, this is exactly what I talked about right now. Yeah, definitely you know what is bias and variance, right? Is there any chance you don't know it? It's okay to ask. Everybody's cool what I mean by bias? I mean, I think I explained it intuitively for you. So just to make sure, because I felt like, yeah, I don't know why I didn't put it like before. Yeah, but I'm talking, to be fair, I'm talking about it later. Okay? But what I mean by bias and variance is that when you have your estimate, so this is the value of one particular policy pi, and you are computing at S, right? Now, if, say this is the, like this orange one is the true value, okay? And then you are just computing one estimate, right? Now, this estimate, as we talked about, you can write it down this guy plus some error, right? You can always write it down in this form, right? So this guy is always the true value plus some error, right? And this error that you see here, if it has zero mean, the average value of this error is 0, then you don't have any bias, right? This means that when you keep on sampling and averaging, the variance of this guy gets smaller and smaller and smaller. Eventually, it gets to 0, and you end up with the exact value that you have, right? But what you see as the estimate is this summation, right? So it means that when you estimate once, you might get somewhere above. When you estimate once again, you might get somewhere below. But eventually, when you just keep estimating for a long time, then this guy is going to be exact, right? Now, this guy could have bias as well, the mean value. So it's not necessarily 0 mean, right? If it has a mean value, it means that when you just converge, the variance is going to 0, but its mean not 0, right? And then you're going to have your true value plus some mean, right? Correct? That is the bias. This is exactly the thing that I told you. So I have it here in this slide for the particular case. So if I have v hat to be the estimate of my value in one particular state, then the average v hat, when I do not have any bias, is exactly the true value function that I have. And this is some property that the Monte Carlo always have, right? Because in Monte Carlo, you are just using independent samples. Every single sample that you are using is eventually the unbiased estimator of what you want. When you average them, they remain unbiased. Okay? So the average value that you get out of your estimate is exactly the value that you have. But in practice, it has a large variance. So it means that when you have a few samples and you do the average, you are landing somewhere around the value, and this around could be very large, right? Whereas in TD, this is not the case. So the average value, the estimate that you get in average is not necessarily exactly like the value that you have. So you could have some bias, but in return, you are just getting smaller variances, right? So it is exactly the same example I told you. If the true value is 1, when you use Monte Carlo, you are just always jumping up and down around 1, right? But you are just taking very large jumps, right? But in the TD, you are maybe jumping up and down around 1.2, but you are jumping smaller, right? So this is the trade-off, right? Because say you have one estimate, right? Just one estimate. You just collect samples and estimate. Then when you have high variance in Monte Carlo, the value is 1, but you might estimate it as 1.8, right? Because you're jumping up. If you estimate from some other data, you might estimate 0.2, right? In TD, you might have 1.2 as the average, but maybe because of the small variance, you end up 1.4, right? And then it's going to give you a smaller error in general, right? So this is the kind of general trade-off between variance and bias. It's not depending on this one. It's always in statistics. When you want to estimate one unknown, you need to deal with the bias and variance, right? Maybe you can reduce the variance at the cost of having a bit of bias. Maybe you don't like to have so you need to take the high variance. For instance, when we are doing deep learning, we usually care about having no bias, right? Because we say when you are doing a stochastic gradient descent, because you would say in every single iteration, I am randomly moving towards the average direction, but if I have a bias, I could just totally diverge in another direction, for instance, right? But in some other applications, you don't care about the bias. You want to reduce the variance, right? So that being said, so yeah. Now let me, sorry, questions? Yeah.
So in TD,
Yeah.
does the variance always come from an incomplete state about the environment? Or like, let's say you're using TD, but you do have in a scenario like the access to the complete Markov state of the environment. In that case, does the variance for TD go down to 0, or is it still potentially variable?
Oh, variance of none of them is going to be absolutely 0. All of them are going to get to 0, right?
So I mean bias actually.
The bias.
Yeah.
Oh, the bias. Whether you can make the bias. It depends on the environment, definitely. So if the environment is, for example, sampling rewards somewhat symmetrically, it might be the case that your bias is 0. So it doesn't mean that you always have bias by TD by itself, because if you use bootstrapping, it could just propagate some sort of error, which they are going to accumulate, and then they're just showing up as bias in return. So that, at the end of the day, depends on your rewarding system. For some specific rewarding system, maybe this is not going to be any bias. Yeah? This might happen, but in general, you cannot guarantee it. Whereas in Monte Carlo, you can guarantee you have no bias. Questions? No question? Okay. So if you got no question, let me just give you a quick overview on this one, and then I'm going to stop here at TD0, so we can just talk about deeper TD next time. So the whole idea of TD was that instead of Monte Carlo, I want to use TD, but at the end of the day, I use this TD to evaluate my policy, right? Once I have TD, I can use it to again implement policy iteration, right? So what I'm going to do, I'm going to do exactly the same as before. So I'm going to start with some policy pi. I just evaluate it using TD, and then given the value that I get, I update or improve my policy, and I put that back to the TD evaluator to just evaluate it again, right? And the greedy algorithm, which is improving, is same thing as before, right? So it's exactly the same thing as we had for the Monte Carlo. Instead of using Monte Carlo, I'm just using TD. This is what I call a TD0 approach. And the reason that I call it 0 is because, as I said, when I am just estimating, I use the value of the immediate next state, right? We're going to see that instead of immediate next state, I can take the value of the second next state, right? And then it might give me a lower bias, but a tiny bit of higher variance, but maybe I like it, right? Maybe it's a better thing, right, as compared to 0, immediate next state. So this is what we call a TD0, and then TD0 is doing exactly like what we do with the Monte Carlo. We start with one policy, we evaluate it. Of course, the evaluation that we are doing here is not exact anymore. Again, this is an estimate, right? And then when I get this estimate, then I am going to get updated by the greedy approach, and I keep on going like this. One thing that you should pay attention to is that here, even with TD, even if you have extremely large number of samples, because you have bias, your estimate might be eventually at the very, very end still different from the value, right? The true value. And this might cause that even if you have extremely large number of samples, you are not converging to the optimal policy. This might be, okay? There is no reason that this is necessarily correct, because estimating different values is not going to necessarily impact your estimate of policy, right? If I estimate value of every direction by a shift of 2, I don't care, right? At the end, the one direction which gives me the largest value or largest estimation is going to be exactly the same as the one which is largest value, right? So the bias is not necessarily doing any harm, but it could cause some harm, right? So that being said, this means that if you use TD, okay, this is usually very good for the case where you have limited number of data. But in practice, you cannot imagine a kind of environment where you have enough data, right? This is why, in general, TD is good, right? So if you had like an environment which is crazy large in number, very small, so that you can collect crazy large number of samples, then probably going for a Monte Carlo gonna give you a more accurate, or at least you can guarantee that you end up with the optimal policy. Everybody's clear, right?